Okay, so now we're going to go ahead and start looking at some examples of laminar motion, which is just a fancy way of saying that our motion is confined to a plane. So I'm going to assume here that we met one of the three conditions in the previous video. So we'll assume one of 1 through 3 is met. And with that, our equations of motions will become the force is equal to m times RCM double dot, and the torque as measured in our theta prime axis will be equal to dl dt, again as measured with our theta prime axis, and we can observe that that would be equal to I calculated about theta prime, about the origin prime, the accelerated origin, times omega dot. Alright, so with that, let's go ahead and do a few examples. It's nothing like breaking out our friendly inclined plane. And this is the first of 2 examples that I'll be doing with that. So we'll go ahead and we'll make us an inclined plane. There we go. Tilted at angle theta as always. And then here is my unprimed origin. And then we'll go ahead and analyze everything about the center of mass. So that's the center of mass right there. So our forces are gravity acting straight down, we'll have a normal force, and there's its point of contact right there. And we'll also have the force exerted by the plane trying to push it back up. Alright, let's go ahead and say that this is of radius A. And we'll look at this rolling through as it rolls down some distance x. We'll observe that it will have rotated through some angle phi. Okay, so with all of that, let's start with our equations of motion. So we have F equals m RCM double dot. So this will give us 2 equations. It'll give us an x equation of motion, so m xcm double dot will be equal to mg sine theta minus our fp, and our y equation of motion will be m y double prime cm equals fn minus mg cosine theta. Now we have our constraint here is that the height of the center of mass will stay a constant above the plane. So ycm equals a constant. So that means that both ycm dot, but more importantly ycm double dot, is equal to 0. So with that, I can write my system of my Newton's second law equations as m xcm double dot equals mg sine theta minus fp, and since this will now go to 0 due to the constraint, the normal force is equal to mg cosine theta. So that's part of my system of equations. I also have my torque equation, so let's look at it. the torque measured about O prime is equal to the moment of inertia about O prime times omega. So the torque will be equal to the force of the plane times the radius, so that's A. That'll be equal to I about the center of mass times omega dot. So that's the third of my equations. In general, this is as far as I can take it without additional information. So let's look at some special cases. Let's go take a look, for instance, at rolling without slipping. So in this case, we know that the force that the plane exerts has to be less than or equal to mu static times the normal force. So in that case, we can observe that XCM would be equal to A times that angle phi I alluded to. So, I mean, XCM dot would be equal to A phi dot, and double dot would also get double dot, which we would observe as A omega dot. Alright, so with all that, from here, from here I can observe that omega, that omega dot would be equal to XCM double dot over A. That's good. But from here I can observe that omega dot would have to be equal to FPA over I moment of inertia at the center of mass. So that tells me that my FP would have to be equal to moment of inertia about the center of mass over A squared times XCM double dot. Alright. So now we can go put that into the X equation of motion. So that'll become mxcm double dot equals mg sine theta minus ICM over A squared XCM double dot. Alright, now it'd be nice if we had an m that we could cancel with. So we'll reintroduce our friend the radius of gyration. So mg sine theta, so the moment of inertia will be equal to, I'm sorry, it's just a minus there. Oops. So it's just a minus there. That'll be equal to m times the radius of gyration squared over A squared XCM double dot. And I can now conveniently cancel all my m's. Alright, so I can then go ahead and solve this for XCM double dot. XCM double dot will be equal to g sine theta over 1 plus k squared over A squared. So armed with that, you should be able to revisit that old chestnut. If I let them all go from at rest, which will get down the ramp first? A sphere, a cylinder, or a hoop? So think about it and I'll get back with you. Okay, so for a sphere, k squared is equal to 2/5 A squared. For a cylinder, k squared is equal to 1/2 A squared. And for a hoop, k squared is equal to A squared. Alrighty then. So let's just follow that thought through. Let's just call whatever the leading constant is eta. So x double dot cm. So this would be eta for my sphere, that would be eta for my cylinder, and for my hoop, eta would be 1. Let's draw a proper eta there. Much better. Yeah, that one's a little dodgy but acceptable, but we'll make it more obvious. There we go. So we'll write that my XCM double dot, now let's move that now. There, that's better. Will equal, will equal G sine theta over 1 plus eta k squared over a squared. I'm sorry, eta a squared. That's the whole point of this. Eta a squared. So we can cancel the a squareds, and I get that's equal to G sine theta over 1 plus eta. So whoever has the smallest eta wins. So that means the sphere is the winner, the cylinder comes in second, and the hoop is dead last. We could probably intuit that better from energy, because since these objects here have more mass further away from the center of rotation, the rotational kinetic energy will have to be greater at any given speed than it is for the sphere. Alright, let's take this a little further here. We'll see eventually that this is our inclined plane for a very special case, but let's just start with it. So let's go take a look at the yo-yo. And again, this will also be part 1. So I have a ceiling, I have attached a cylinder to a string like so. Again, radius A, so I'll have a force of gravity, and I'll have an upward force of tension, and that's about it. So we can look at the y equation of motion. And here I think it'll make sense to choose down to be positive. So we'll say that my double dot cm equals mg minus t. There is no x equation of motion, so we go straight to rotations. The torque is equal to TA. That's be equal to ICM omega dot. We do have a constraint. Our constraint is that YCM double dot has to equal A omega dot. Alright. So plugging in for that constraint, we can say TA is equal to ICM times YCM double dot over A. So we can write the tension as being ICM over A squared YCM double dot, or bringing back up from the radius of gyration, k squared over A squared YCM double dot. Alright, so now we can plug that back into Newton's second law there and get m times YCM double dot equals mg minus mk squared over A squared YCM double dot. And so we get, after we cancel our m's everywhere, that YCM double dot is equal to G over 1 plus k squared over A squared, which makes a lot of sense because this corresponds to an inclined plane that's been tilted at 90 degrees. So it's exactly what we expect. Alright, so I think we've beat the equations of motion to death as best we can. Let's go take a look at this from an energy perspective. So from energy, we still require that the total mechanical energy be a constant. And we'll say if we have motion and gravity and we have, none of our other forces do any work, this can become like a 1/2 m xcm dot squared plus 1/2 ICM omega squared plus, say, mghcm equals E. Now, if there are other conservative forces, obviously we'll have to add other terms. The main thing is we don't want any non-conservative forces in this analysis. So let's redo the yo-yo. Part 2. All right, so following the same free body diagram that we just had, we can write that 1/2 mycm dot squared plus 1/2 ICM omega squared plus mghcm equals E. Alrighty. So following the prescriptions that we've had before, we're choosing down to be positive, so we can write this as 1/2 mycm dot squared plus 1/2 mk squared over a squared, just like before, ycm dot squared plus, minus, because down is positive, minus mgycm equals E. So that's just doing the same prescription that we've done before. Now, if we're clever in our choice of y setting our 0 for y, I'll choose to make YCM 0 at the point where I let it go. By doing that, I can make the total mechanical energy 0. I'm always free to do that anyway. I can always shift my potential energy by a constant. So I could just said I'm shifting it in such a way that E is 0. Alright, so with that, I can go and divide everybody through by m and make the m's go away. That's something. And so let's see, we'll get a 1/2. I can group the YCM dots, so 1 plus k squared over a squared YCM dot squared minus g YCM equals 0. Okay, now the trick here to take this further, like we've done before with we've solved with energy, is if I take this whole expression and now differentiate it with respect to time, I'll have a 1/2 1 plus k squared over a squared. Differentiating this is going to bring me a 2 out in front, so I'll have YCM dot, and I have to differentiate what's inside, YCM double dot minus GYCM dot equals 0. Okay, I can divide both sides through by YCM dot, and then I am left with YCM double dot is equal to G over 1 plus k squared over a squared, and then we know where this goes from there. Alright, and we can go ahead and do this same kind of thing again with the inclined plane. So the only real difference here is our y's become x's. Well, cancel. Our y's become x's, so we get 1/2 x dot squared cm. Oh, let's quit writing the cm. There's no real need for it. There we go. 1/2 m x dot squared plus 1/2 m k squared over a squared x dot squared minus mgx sine theta equals 0. This is for the same free body diagram that I drew back in the day. So again, I can divide m's out everywhere. Then I'll go ahead and differentiate with respect to time. So I'll get 2 times 1/2 times x dot x double dot plus 2 times 1/2 k squared over a squared x dot x double dot minus g x dot sine theta equals 0. Cancel, 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 cancel. And we can, everybody's got an x dot that we can divide out. And I end up with x double dot equals g sine theta over 1 plus k squared over a squared. And the rest of it goes like before. All right. Now you may be starting to suspect, and I'll just say your suspicions would be correct, that that apparently maybe we can be more general with this energy analysis and come up with a way of getting the equations of motion in general. And your suspicions would be correct. We're going to have to wait until we get further along in the course, though, before we do that. Now, at this point, you should be getting a little concerned, maybe, about the fact that I neglected the tension in the case of the yo-yo, and the normal force and the force of the inclined plane in the case of the inclined plane. So the easy one first. For the normal force, it's perpendicular to displacement, and there's no work being done. Now, for the case of the tension and the force of the inclined plane, so let's look at the tension here. There is a subtle flaw in what I'm about to say. I'm about to state it the way most books say it. There is a subtle flaw to this, and I will let you stew on it. I'm not going to give it away in the video. But I will let you stew on it and see if you can come up with the flaw. Anyway, the idea sort of goes like this. If we go and look at the point of contact right there, at that point right there, the point of contact isn't moving. And so that's good, because that means we're applying the force, these forces, at a point where the speed is 0. So we know that power is equal to force dot of the velocity. If the velocity is 0, that tells us that the time rate of change of the work is 0. So that tells us that the constant, that at most these things can be doing constant work, but the point of contact isn't moving, so that constant is 0. Okay, there is a flaw to that argument. It's a very subtle flaw. Like I say, you can think it through and you can catch up with me later on it and see what we think. But for now, I'll at least say this. In any event, we know that when we do these things, the object doesn't get hot. So that tension or that work done by the plane must be 0 anyway. Alright, so I think we have pushed rolling without slipping as far as we possibly can. So now let's look at the case where we are slipping. Alright, it has been... Let's go draw another inclined plane just so we can visualize a bit. So, again, there's my inclined plane. There's my thing rolling down at. Force of gravity. Normal force. Force due to the inclined plane. So here, the force due to the inclined plane will be equal to the coefficient kinetic friction times the normal force. And we've already worked out the normal force is mg cosine theta. Alright, so then my x equation of motion will become mx double dot equals mg sine theta minus mu k mg cosine theta. And we can cancel m's all around. We also have that for our rotations, we can say that I omega dot is equal to the force of friction. That'll be mu k mg a, sorry, mg cosine theta times the lever arm, which is a. All right. So with that, we can go ahead and do the same trick of saying this is mk squared omega dot kmga cosine theta. And doing that, we can cancel the m's. So we are left with omega dot equaling mu k times g over g, whoops, try this again, mu k g a cosine theta. Normally I would divide the whole thing by k squared, but I'm just going to divide the a by k squared. Alright, now here we can relate our x double dot and our omega dot. We can't do it as cleanly as we did before, so I'll just define gamma to be the ratio of x double dot to a omega dot, because that's as best as we can do. And we can get an expression for it. It'll be g times sine theta minus mu k cosine theta from Newton's second law over mu k g a squared over k squared cosine theta. Okay, and we can cancel the g's, so apparently it doesn't matter what planet we do this on. Alright, so we know that gamma has to be less than or equal to 1. The reason there is gamma equals 1 is rolling without slipping, and then at that point we would have to replace our mu k with mu s. And so for anything less, in order for it to be mu k, then gamma would have to be 1, so less than 1. So we can write anyway our x double dot is equal to gamma a omega dot. So going from before, we can write omega is mu k g a over k squared cosine theta. That was omega dot, right? And we're just going to integrate that with respect to time, so we just pick up a t. And then playing the same game with our x dot here, we said that that is equal to gamma a omega dot, right? So that will equal gamma mu k g a squared over k squared cosine theta. T. Yeah. He was dropping something there. Alright. So anyway, with all of that, alright, yeah, we're just taking the result from before. Alright, so with all that, we can then ask, say, what is the minimum mu s to roll without slipping? Well, that would be requiring that gamma equal 1. That would equal sine theta. Now this would be minus mu s rather than mu k cosine theta over mu s a squared over k squared cosine theta. So we can solve that for mu s. That'll equal the tangent of theta over 1 plus a squared over k squared. Cool. All right. I would like to conclude this video here by revisiting example 8.6.2 from your text. So in this example, you have a large cylindrical impression and you're rolling a cylinder, although I'll try to be more generic at first anyway. You're rolling a cylinder in it. So it's rolling at omega. We'll call that point right there point P. We'll say the radius is big R. So take it back. We'll say that the radius is little r, and we would be putting our unprimed origin right there. Okay. So if we go and draw a free body diagram for our cylinder, right, we're going to have a force being applied by the surface. We're going to have a normal force, and we'll have a force of gravity. Okay, so that's enough to get us rolling here. Write our equations of motion, so mx double dot will equal minus mg sine theta. There, that's theta. Minus mg sine theta plus our f, and my double dot will equal, which is going to be equal to 0 due to our constraint, will equal Fn, normal force, minus mg cosine theta. So this tells me that Fn is equal to mg cosine theta. So what we've got really here is a continuously varying inclined plane, if you want to think of it that way. All right, so we can write I omega dot is equal to Fr. So that will be minus, to get the directions right, k squared x double dot over r equals Fr. So we get that F is equal to minus mx double dot k squared over r squared. We can do that because we got the constraint here that minus x double dot has to be equal to r omega dot. Okay. So Newton's second law becomes mx double dot equals minus mg sine theta minus mx double dot k squared over r squared. And we can cancel all those m's away. And we are left with x double dot times 1 plus k squared over r squared plus g sine theta equals 0. So we can go ahead and do the usual tricks. We can let theta be approximately equal to small, so the I'm sorry, I don't need to do that just yet. Yeah, we can do that. So then my x double dot will be equal to r minus r theta double dot plus g theta, and we'll divide by 1 plus k squared over r squared. That equals 0. Alright, so for a cylinder, recall that k squared is equal to 1/2 r squared. So then this will become theta double dot plus g over 1 plus 1/2 r squared over r squared, cancel, cancel, r minus r, theta equals 0. Let's clean that up just a bit so we can look at what we're doing. So you get theta double dot plus g over 3/2 r minus r, oops, times theta equals 0. We look at this and say, hey, that's a pendulum. Specifically, that would be the same motion as a pendulum whose length was 3/2 of r minus r. Okay. Now the book did it a different way. They did energy. So just show that there's more than one way to skin a cat. We'll say that the energy, which is equal to kinetic plus potential, is 1/2 I omega squared plus 1/2 mx dot squared plus mgh. Okay, so our h is going to be equal to r minus r times 1 minus cosine theta. We've worked that through before. And so we'll say that that's approximately 1/2 r minus r theta squared, keeping from the first two terms of the Taylor series of cosine. Okay, so you can also say that omega is equal to x dot over r. So this will equal r minus r over r theta dot. Okay, so with all of that, we can write our energy as 1/2 m k squared over r squared, r minus r squared theta dot squared, plus 1/2 m r minus r squared theta dot squared, plus 1/2 mg r minus r theta squared. And we can differentiate that with respect to time. So the energy is a constant, so differentiating all this with respect to time gives me that as a 0. So here I get mk squared over r squared, r minus r squared, theta dot, theta double dot, plus m r minus r squared, theta dot, theta double dot, plus mg. I'm sorry, this is r minus r there. No need to square. Oh, I'm sorry, that's the theta that's squared there. Okay, there we go. So this is mg r minus r. This becomes theta dot. Alright, so we can cancel all the theta dots. And we can cancel 1 power of r minus r. And rearranging, we get that 0 is equal to r minus r times 1 plus k squared over r squared theta double dot plus g theta, and the rest is just like we did before. Okay, the next video we will briefly look at impulse and collisions with specific attention to the baseball bat theorem.